Hello 115 students. It's time for some further discussion about properties of solution that were discussed somewhat in Chem Activity 29B, and the point is, how do solutions differ from pure solvents in their behavior? And these are described in a general sense as colligative properties. These things are the properties which depend only on the number of particles dissolved in the solution, not on their nature. As discussed in class, this would be particles, meaning there can be either ions or molecules, and so it depends on the number of these present in the solution, no matter which they are, whether ionic or molecular. The thing to recall and keep track of is that ionic compounds will always contain more moles of ions, more total moles, than they do of the compound. So when they're dissolved in solution, ionic compounds have more particles per mole than do molecular compounds. Be mindful of what was discussed with the electrolytes handout in Activity 14 in the Popel book. One of these colligative properties, the first one, is called vapor pressure lowering. In other words, vapor pressure is that pressure that you get when there's gas molecules above a liquid in a closed container. Only the blue ones here are the vapor pressure molecules. The red ones refer to solvent in this case, or reflect the solute. And so the vapor pressure is due to the presence of solvent molecules in the air above the liquid. Vapor pressure can be measured with the U-tube device, that manometer kind of thing, open-ended manometer, and the vapor pressure is always going to be lower for a solution, than a pure solvent. So on the left we have a solution where you have solute involved in the beaker, and on the right is a pure solution. And so the side of the mercury open to the air is lower on the left example compared to the right. It's higher, and that means that this one has a higher vapor pressure in the pure solvent. The one with the solution, with the solute present, has a lower vapor pressure due to the fact that this is a colligative property, namely the ability of solvent molecules to escape to the gas here is dependent upon their getting away from the surface, and literally solute particles interfere with their being able to escape at the surface of the liquid phase. That results in the lowered equilibrium vapor pressure. Now, who cares? What's this vapor pressure got to do with anything? Well, if you recall from the end of chapter 8, vapor pressure is related to boiling points. And if you remember the definition of a normal boiling point is the temperature at which external pressure is equal to the vapor pressure. And a typical external pressure is 1 atmosphere, or 760 millimeters of mercury. And so looking at these two vapor pressure curves, they always increase. The vapor pressure increases as the temperature increases, so you have these upward curving lines. And the red line and the green line, one is a solvent and one is the solution, but we have to determine which one is which. This is an example from the text, but we're going to talk you through it. So first of all, look at the boiling points of these two things. And the boiling point is that point on the vapor pressure curve where the external pressure equals the vapor pressure. In other words, ordinary pressure. So at 1 atmosphere, or 760 millimeters of mercury, the red line has a boiling point of about 64 perhaps. Wait a minute, that's not 64. That's 65 in the middle, so this must be maybe 62. And so the green line, the point at which the vapor pressure equals external pressure, or ordinary external pressure, would be where the green line intersects with the 760 millimeters of mercury. And judging from this graph, make an estimate, it might be 68, or somewhere between 68 and 69. Hard to say, doesn't matter at this point, but it's higher for the green line than the red line. In other words, one of these is a solvent, a pure solvent, and one is a solution. Recalling what was described on the previous slide, the vapor pressure is going to be reduced at a particular temperature for a solution. And so if you compare these two lines, the solution must be the green line because it has a lower vapor pressure at any particular temperature due to the presence of solute molecules. So the approximate boiling point of the solvent is the red line, where the red line crosses the 760. So that would be approximately 62, just an estimate here. And for the solution is going to be somewhat higher. It's that value we estimated to be somewhere around 68. So you can identify which is a solute and which is the solvent, which is the solvent, which is a solution containing solute, by looking at their vapor pressures. Again, the vapor pressure is reduced, which is why the green line is lower, for a solution. All right, has to do with the fact that solute molecules interfere with the escape of solvent from the surface of the liquid. The second colligative property is called boiling point elevation. This one was discussed in Chem Activity 29 in the POGIL book, 29B, sorry, and so you can refer to that in your textbook, in your POGIL book as well. And it is related to this vapor pressure concept. Because vapor pressure, and since vapor pressure is lower for the solution than the pure solvent, the boiling point of that solution is therefore higher than that of the pure solvent, which is exactly what was observed on the graph on the previous slide. So the boiling point of a solution is higher than a pure solvent. That's why we call this boiling point elevation. That's the name of this property. And so that tells you that it requires a higher temperature to get the vapor pressure equal to the external pressure, which is when the liquid will eventually, the liquid, whatever it is, solution or solvent, is going to boil, when the vapor pressure equals the external pressure. For water, for aqueous solutions, the boiling point is going to be raised about 0.5 degrees Celsius for each mole of solute in 1 kilogram of solvent, and for most purposes, the kilogram of solvent is essentially 1 liter. We're not going to look at the specific examples where that's not the case. And so that's equivalent to what you saw in Chem Activity 29B. If you recall, it was the temperature was going to increase, the boiling temperature increased about 0.5 degrees Celsius for each mole of solute per liter. And so that's for these kinds of things we relate to molarity. So if you can recall some examples from class in the Chem Activity, which boiling point will be higher? The sodium chloride, 1 molar sodium chloride, or 1 molar aluminum chloride? Well, you have to remember how many moles of solute each of these contain. 1 mole per liter of sodium chloride has 2 moles of ions, and that's because you have 1 mole of sodium ions and 1 mole of chloride ions. And the number of moles of solute for the aluminum chloride is a total of 4 moles of ions, because you have 1 mole of aluminum and 3 moles of separated chloride ions. And so each of those, they count separately as particles in the solute conversation. So the one that has the most moles of solute per liter, per kilogram, works out the same, is going to be the one that has the higher boiling point. The higher boiling point, therefore, is the aluminum chloride. All right, the third colligative property is called freezing point depression. In other words, solutions are going to freeze at a lower temperature than pure solvents. For water and aqueous solutions, the ones we refer to the most often, the melting point, aka freezing point, is lowered about 1.9 or 1.86 degrees Celsius. In the POGIL book it was shown to be about 1.9, but we weren't using as many sig figs as this one. For each mole of solute particles in 1 kilogram, again, 1 kilogram is per liter. And so for aqueous solutions, that's a reasonable approximation. It's not really cheating. And so the melting point, freezing point, is going to be decreased for every mole of solute particles in a kilogram of solvent. How do we use that? Well, as I have been known to joke, freezing point depression is also a note to photopsychosis, what happens to us when the weather is cold, especially when we're hoping for spring. In other words, the solutions are freezing at lower temperatures than pure solvents. Now, the melting point of water is lowered for each mole of solute particles in a kilogram of solvent. So that's why putting salt on ice works. It lowers the freezing temperature of the water on the sidewalks or wherever it is, and keeps it liquid and not slippery to a lower temperature than just the normal freezing point of water. While sodium chloride and calcium chloride can both be used, as was discussed in the POGIL activity. So if you compare some other compounds, 1 molar sodium chloride, 1 molar calcium chloride, and 1 molar aluminum chloride, which one is going to lower the freezing point of a kilogram of water the most? In other words, which one has the greatest effect on the freezing point? Which one lowers it the most? Again, it has to do with how many moles of solute particles per kilogram of solvent, aka per liter. And so the number of moles of solute particles for sodium chloride is 2, 1 sodium, 1 chloride, 2 moles of ions per liter per kilogram. For calcium chloride, there's 1 calcium and 2 chloride ions, so it's a total of 3 moles of ions. Because these things are soluble and dissociate completely in water, you get 3 moles of ions. Aluminum chloride, just like it was an example with the boiling point elevation, this will be 4 moles of ions per liter, and therefore this one has the most moles of solute particles per kilogram of solvent. The aluminum chloride is definitely going to lower the freezing point the most in this example. All right, now the last colligative property to mention a little bit is osmosis and osmotic pressure. We discussed osmosis recently in the POGIL book as well, and the day we were describing hypertonic and hypotonic solutions. Osmosis requires membranes. You have to have a membrane to separate different solutions, and membranes are like a very thin sheet with holes. There are various types: permeable, semi-permeable, and impermeable. Impermeable is like a mylar balloon that basically doesn't leak. A permeable membrane is something like a mesh that anything can get in and out of. The ones that are used for osmosis are going to be semi-permeable because they only allow the passage of smaller molecules such as water or other solvent molecules or things of a similar size, and things like nitrogen, oxygen, or CO2. So osmotic membranes are semi-permeable and only allow certain things to flow through. Osmosis, as was described in that chem activity last week, has to do with the flow of water or other small solvent molecules across a membrane and nothing more. The solute molecules don't go anywhere. And the water is always going to go from a more dilute solution towards a more concentrated solution. The movement of water effectively reduces the concentration of the more concentrated solution. Now, this has everything to do with those examples with the eggs that I showed you. And as you may recall, I showed you what they look like after they've been sitting in vinegar for a day. And one thing noteworthy is to realize what's happening in this reaction with the vinegar. It's noteworthy for chapter 10 as well. What's happening? It's an acid-base reaction. Now, what did I tell you was in there? Vinegar. Vinegar is an acid, and vinegar contains acetic acid that you've heard about a time or two by now. That's a weak electrolyte, and we always have trouble recalling its formula, but it's CH3COOH, which is reacting with what's in the shell. Well, the shell is the base, and the base of the shell includes calcium carbonate, which you've used in laboratory experiments with acids, and calcium carbonate, CaCO3 plus 2 ion minus 2 ion comes out even formula, nothing more to add. It is going to react with the acetic acid to form a lot of bubbles. Well, what do you suppose the bubbles are? Think in terms of these cations and anions swapping. There's a minus 1 ion here and a plus 1 ion there, a plus 2 ion here, and a minus 2 ion here. So swap the minus and plus options, and that will give you calcium with the acetate ion. You've probably forgotten acetate, but it's in your list of polyatomic ions. And we saw it a little bit when we were looking at the electrolytes handout recently. and acetate, whoops, will be present in pairs to go with calcium. Then the remaining ions are the hydrogen ion and carbonate. And to make that formula come out even, it requires 2 hydrogens to go with the carbonate. Well, this is one of those funny things, and we'll discuss this more in Chapter 10, that doesn't ever really occur long enough to be found because it immediately dissociates to make water and carbon dioxide. So that is what explains all the bubbles that you see in this reaction, in this picture of the eggs. So all those bubbles are the carbon dioxide gas that evolves in this reaction. Now, did I balance this? I bet I didn't. So make sure we've got this balanced. You've got to have 2 hydrogens here. 2 hydrogens in the H2CO3 has to mean that there were 2 acetic acid molecules to begin with. And then that gives you an explanation for the 2 on the subscript of the acetate. And that should give you a balanced equation if you look at it closely. Okay, so acid-base reaction is interesting. But once you're done, you end up with eggs that have no more shell. And all that's left is aqueous calcium acetate, a lot of bubbles, and some more water. It smells funny, but that's okay. Now, what happens with these eggs that have now no more shell, but the amniotic membrane around the egg, it's like what you see when you peel a hard-boiled egg, is free of a shell, and you place the shellless egg into 2 different solutions. This picture represents what happens to them when you put one in distilled water and one in corn syrup. In the case of the distilled water, which is on the left, the water is flowing into the egg, going to flow into this side of the membrane that has the greater concentration of solute, and so the egg tends to become larger. It looks like it's swollen. The water goes in. Water is the only thing passing through that osmotic membrane that surrounds the egg. In the other case, on the opposite diagram here, the water is leaving the egg and going into the corn syrup because the corn syrup is very, very dense, very high concentration of solute, very, very little water in it. And so the water leaves the egg, and the egg ends up looking more shriveled, more smaller after you have allowed some osmosis to take place. So again, in each case, the water is going towards the side that has the most solute, and this is requiring a semi-permeable membrane. The application of this that's also more interesting to everyone, I hope, is blood plasma, and the fluid surrounding blood cells requires a osmolarity of 0.30. In other words, that's the same thing as 0.15 molar sodium chloride. That was calculated when we were talking about isotonic, hypertonic, and hypotonic recently with our POGIL activity. And so because sodium chloride has 2 moles of ions per mole of compound, the osmolarity is twice the molarity. So if you're looking for something that's going to be a safe place to put blood cells, you want them in a solution that is isotonic. In other words, 0.3 osmolarity, aka 0.15 molar sodium chloride, or anything else that has 2 ions. If the cells are placed in a solution that is not isotonic, equivalent to the concentration of solute in the cells, you might end up with a hypotonic or a hypertonic solution. A hypotonic is what happens when it's less concentrated than the inside of the cells. It's analogous to my egg in water picture. And the water goes into the cells as shown by these swollen looking cells in this picture, and eventually can cause them to rupture. Lysis means to rupture. Hemolysis is rupture of blood cells. So when the solution has more water and less solute, the water will go into the cells, causing their potential rupture. If the opposite is true, the solution is around the cells is hypertonic. That means there's more solute outside the cells, and so the water is going to tend to leave the cells, leaving them shriveled, and the name for that is crenation. It's a funny word, but it's interesting. It's a way of describing these shriveled blood cells. And so crenated cells are in hypertonic solution because the water is leaving the cells to go to the side of the membrane that has more solute. All right, here's the end of our conversation about colligative properties. I hope that helps you as you work on your homework. Make sure you do as many practice problems as possible and let me know if you have questions.